Later on, we prepared the fibers of sodium, and after obtaining of the optimum condition for sodium inclusion, we decided to add some silver, metallic silver, in order to enhance the superconducting properties. Now we know bismuth-based superconductors, given this formula, has three phases. And the first one is bismuth 2201 phase, has a 1520 K Tc value. And N2 2212 has a between 80 and 96 Kelvin, and 2223 phases has a 150 K. Because of the stability of N2 phases, most of the people are studying on these materials. Okay, let me go further. What we aimed before we studied this project, sodium and the calcium's ionic radius almost the same. Due to this similarity, we decided to replace, substitute sodium for calcium in order to make some changes in their structure, crystal structure, and we aim to change in carrier concentration. As I explained, we decided to prepare, we have found the best condition for sodium inclusion 0075, and we fixed this the main matrix, and we have added 0, 1, 3 and 5% of silver in order to see the variation of the structure. We have prepared our powders by using polymerization technique, following it by directional ground using laser flattening zone technique, and then after preparation of the sample, we investigate the structure and other properties. I will mention about the shortly from polymerization technique. In this technique, acetic acids and the distillated water are using. Then after obtaining the solution, just in medium of this experiment, we are adding polyethylamine in order to polymerize the solution, then drying, burning and milling. Then thermal treatment is applied. The disadvantage of this polymerized solution, only the long time for drying and burning. The other is has an advantage comparison to other techniques. Short thermal treatments, homogeneous products, and small particle size obtained. And after we have powders, in order to obtain the fibers, we have isostasically pressed in the form of cylinder between 2 and 3 millimeters diameter by applying 200 millipascal. We used LFZ system with a continuous power niobium YAG laser with a 1050 nanometer wave. Also, during experiment, we, according to our knowledge, 30 millimeter per hour was the best results. Therefore, we have applied 30 millimeter. We have grown our sample with a 30 millimeter per hour. And the others, after the operation, we were obtaining 120 millimeter length and to 3 millimeter for diameter. In order to protect from the secondary phases, like 2201 bismuth pure part, this one, and the calcium copper oxide, we apply thermal treatment to our fibers. Now let me come to results. Firstly, we have measured their XRD, and I would like to show this part. This is around 36, and this peak was related to one diffraction plane of metallic silver. When we look at this part, it is increasing by increasing of silver content. The others almost pure 2-to-1-2 phases. And we have calculated the crystal parameters A and B, 5.43 angstrom, and for C, 33.63 angstrom, which was good agreement with the normal 2-to-1-2 phases given in literature. Let me come to the some photographs of our samples, and I would like to point out here, this is the pure sample, contain only 1, 2, 3 phases shown in the picture. One is bismuth 2-to-1-2, almost 2-to-1-2 phases, the gray one, and the 2 is black one, bismuth pure phases, citronesium, calcium, copper oxide, and 3 shows the bismuth 2-to-0-1 phases. By increasing silver addition, and we can see here 4 and 5 extra phases, secondary phases. 5 is corresponding to metallic silver part. 4 is another a little bit dark gray, another superconductor phase, indicating by 2 bismuth 2 strontium 2 calcium 0.9, a little bit increasing of sodium amount, and the others the same. Also, this important change appearing at the higher amount of silver arising from the molten zone promoted by the formation of isolated liquid silver particles and all around the melt part, producing this modification in the solidified interface. We have measured magnetization. This is the field-cooled magnetization, and for the samples shown here. And I would like to show here the onset temperatures of the samples, just around 92 Kelvin in all cases, but for this is the pristine sample, it is a little bit lower than the substitute added one. The magnetization curves for 3% of silver samples clearly confirms our SEM observation, showing better quality, homogeneity, and the grain alignment comparison to the other inclusions. Later on, we have measured all samples, magnetic hysteresis of all samples for different temperature interval. You can see by increasing the sodium amount and the area of loop is increasing, the pristine sample has a very lower area comparison to the silver addition. And by increasing temperature, you can see here, the area of the loop is getting lower. And from these figures, we have analyzed remnant magnetization and the critical field, and we have tabulated here. You can see that 3% of the silver has a big magnetic remnant magnetization and also critical field here comparison to others. Later on, we have to want to see just to see the temperature independence of our best sample. This is the expected behavior by decreasing temperature. The loop is getting narrow, and the best one is again 10 Kelvin, and we have already tabulated the results taken from the experimental results like here. Now we have calculated critical field, critical current density by using Bean model, and the formula is given like this. Again, for all temperature interval, we have calculated and tabulated the graphs. You can see the best critical current density is belonging to 30% of silver, as you see in our graph. I would like to show here this part, pure and 1% of the silver and comparison to 3% of silver is almost 2 times larger than the pristine one. Now, this is the new results. We have already measured. 2 months ago, we have analyzed it. Now, still is ongoing, calculating some parameters. The magnetoresistivity of our samples in order to see flux creep model and their behavior in magnetic field. As you see, here's 0.1, and resistivity is dropping and decreasing. By increasing applied magnetic field, the TC offset, called the TC offset, is shifting towards the lower temperature. This is the general behavior of bismuth 2212 samples, high TC bismuth samples. Then by looking at these pictures, we have analyzed and deduced our TC onset, TC offset, and the critical field from the figures. As you see, the TC onset doesn't change so much. Look here. And for all applied magnetic field. But I would like to put emphasis here, TC onset temperature is changing by increasing magnetic field, drastically measured, changing comparison to onset one. This is the part to be investigated. In order to better understand the effect of sodium substitution together with silver addition on the activation energy, we used thermally activated flux flow model, and according to this model, the tail part of protons obeys the, oops, sorry, what happened? Okay. Obeys the Arrhenius law, and the Arrhenius law is given with this formula here. Rosseffer's exponential factor, U is activation energy or flux spinning energy, Kb is the Boltzmann constant. U value can be obtained from the tail part of these figures by plotting slope of logarithm resistivity versus 1 over T graph, and the slope is given the U value. From this graph, we have deduced
2 minutes,
U
please.
activation energy.
Bekir, 2 minutes.
Okay. Activation energy calculate, and you can have a look. The best one is again 3% of silver, and the most of rapidly decreased by increasing applied magnetic field, and U value also increases with silver addition up to 3% of silver. Now results, and I would like to summarize my presentation. XRD pattern show the major peaks are related to 2-to-1-2 phase. In addition, peak intensity at 33.3 increases with increasing silver addition. SEM and EDS results support the XRD results. The magnetic result, JC, and activation energy values of 3% of silver are better than those of the other samples. I would like to thanks to my colleague Andres Sotelo, Maria Madre, and my PhD students for this good collaboration and for the good results. Thank you very much. 25 millimeter. Here you can see about micrometer. This part is silver addition. But
I mean,
we will
the initial powder properties you added to the initial mixture. Was it a silver powder or another form?
Silver powder, yes.
What was the particle size distribution of that powder?
Metallic silver, not powder. It was metallic silver.
But it was dissolved in acid,
Solid.
so you have it in the solution.
So you took it into the solution.
Yeah.
Acid solution.
Yes.
Understand. And did you have any? This is the second question. Did you observe any copper alloying with silver? Because when you have copper atoms into the matrix at high temperature, they tend to alloy with silver. Did you observe such a phenomena?
No, we have not observed such a kind of phase.
Okay, I did some experiments on this issue some years ago. A couple of microns layer is influenced by the copper migration. I mean, it's some sort of, you get some sort of silver copper alloy when you heat treat the sample at high temperature. That may slightly change the local copper content of the sample, copper stoichiometry of the sample. Anyway, thank you.
Thanks.